as said, my name is Max, and I'm today here with Pallavi to talk about quantum computing for enterprise adoption. And compared to the talks we had, or most of the talks at least, we had the last few days, I mean, we are really one or maybe also even two levels ahead of most of the details we spoke about. But it's maybe also a good opportunity to start a discussion about, I mean, where this potential interlock between the application layer and then the system software and the hardware might be. And that's what we will present. As a quick disclaimer, I mean, whatever you see today is early prototypes, so nothing is available publicly yet. And it's, of course, I mean, subject to change within this environment. There's always changes, and it's in the end our current train of thought, how we think, how we see the world, and should give you a good impression what we do within SAP. To the two of us, we are part of the business technology platform, so in the end the cloud platform of SAP, which is why we have some special thoughts on, I mean, how we could potentially enable our LOB solutions with quantum technologies, but that's what we will then also later on come to. Pallavi is our quantum machine learning lead within our team, and I'm the product manager, even though we do not yet have a product, which is sometimes then hard to argue that I'm already the product manager. With that said, let's have a look at the agenda. I'll quickly talk about what SAP actually is, but I will really keep it short, but it's maybe also interesting to then get the later thoughts why we see the world we see it and why we do the things we do. But I really keep it very, very high level. And then we will come to the point what we do within quantum computing and SAP, why is it relevant and in which areas is it relevant. And then also have a quick discussion about, I mean, what our first initiatives within our team are. So we are the team of quantum exploration. That's our name. And then the interesting part will begin at the second and third main point with the strategic initiatives. When we speak about, I mean, how we see quantum computing for SAP business applications evolving in the future. And we really have a very high level glimpse into how we could foresee the architecture. I mean, this is also here on a very high level. But I said it might be a good starting point for a discussion. And then Pallavi will take over for the last point, which is then an implementation deep dive of one of our use cases, which will be tabular data generation. And yeah, we will have a quick use case overview, discuss, I mean, how we approach it, research results, and then also there having a quick look into what kind of tools we use, which might be then also of interest for this audience, and then we'll sum it up as some kind of key takeaways. With that, what is SAP? SAP is the world's largest enterprise application software vendor. We cover 26 industries, 12 lines of businesses, so pretty much every business process you can think of, there's a good chance that we will cover it. We have a huge customer base from, of course, I mean, the big players, but that's often a misperception that SAP is only serving large-scale enterprises. That's by far not the case. So around 80% of our customers are actually small, medium-sized enterprises. The footprint globally is quite broad, so it's estimated that around 87% of the total global commerce is generated by SAP customers. And we, of course, also heavily investing in AI, where we already have 27,000 customers using our AI portfolio, and we are more and more also speeding up in the cloud, so with already 300 cloud users. And our total revenue 2023 was plus 31 billion, but that only is a quick intro. I mean, the key thing, what I wanted to do, why I added this slide is on the one hand side, I mean, we really cover pretty much all of the business processes, a lot of industries, and really the entire scale from large-scale customers, but also to the smaller levels. And then to quantum computing at SAP. In the middle, you see our portfolio, and that's also, I mean, where we are then coming from. So we are here from this business technology platform. That's where our team is residing. This doesn't mean that we are the only people who are looking into quantum computing. So there are also other teams like the optimization team who are also doing a great job, who are then even a step closer towards the actual business applications. And what we are trying to assess is, what kind of reusable services do we need to provide in order to then enable our entire portfolio with quantum computing. And what we focus on, not surprisingly, I mean, the three domains down below: machine learning, optimization, simulation. For simulation, we need to be a little bit careful, because where we do not focus on is really the simulation of complex quantum systems, like for material science, drug discovery. I mean, this is out of scope for SAP. When it comes to the simulation of business processes, so supply chains, production programs, etc., then it's of course something which would be relevant for SAP, and that's why we are looking into it. but nothing really regarding material science, etc. And the key message also from this slide is, in the end, I mean, we try to depict a couple of use cases we would foresee. And these are all coming from the entire portfolio from SAP, so ranging from supply chain, finance, manufacturing, even HR to a certain extent. And we really see this potential. I mean, this does not mean that we, all of the use cases we see would then really be maybe a perfect fit for quantum computing. That's something we need to investigate. We also by far did not investigate all of them, but I mean, the potential and the use cases we have at hand are really huge, so there's a lot of opportunities we can engage and have a look into. And when we then look at what we do and what we focus on, maybe first, I mean, our vision is, of course, I mean, that we at a certain point in time empower this quantum-ready enterprise of tomorrow. And if you look at the SEC where we are focusing on, it's really only this very top layer. It's in the end the business applications, of course, which is owned by us. And the question, I mean, how do we integrate with them? But then, of course, also having a look at the problem modeling and the quantum algorithms. But then we usually try to stop and rather partner them in the lower level. So we would not just ever now create or develop our own compiler or whatever is needed then on the lower levels. This does not mean that we at the moment always stop here. I mean, we are also looking into topics like optimization of algorithms for hardwares. We're looking into the topic of error correction, but this is something which we do as it's not yet readily available. So this is something we would rather long-term see to be provided either by the hardware vendors directly or then by a middle layer within between, so that we can really focus on this top layer, ideally. I mean, when and how this would then come true is then, of course, maybe also with a small question mark, but we really try to keep it on this highest top layer. And what we currently do is we explore use cases across the portfolio of SAP. So I later on also have a slide that I get an overview of what we're currently investigating. And we are building these small-scale prototypes where you would also then later on see one of our first use cases. And the key thing is what we are trying to align and come to is really an aligned architecture, so that we have one central integration, for example, for the hardware platform, so that not every individual product within SAP or every individual LOB would need to come up with an own solution, but that we really have the scale, and we only need to do it once, and not everyone have then this effort multiplied, and of course then also reduces the effort tremendously. Goal is then in the end, I mean, with all of this, the architecture, the prototypes, that we really have the entire end-to-end process under control, from the business application, the use case, hopefully also at a certain point in time the value add, so that whenever the hardware is ready, we can flip the switch and then go for live productive solutions. And then to the interesting parts of the strategic initiatives. This is once again, I mean, a very high-level picture how we could foresee the world, and we try to differentiate. I mean, on top you see the business applications, and then on the lower level, I mean, this ecosystem, so hardware vendors, but also to a certain extent system software, whereas they are also then spilling over towards the top layers. And what we try to understand and investigate, if we could really in the end position BTP as this connecting layer between the actual business applications and then this quantum ecosystem. And we see three main layers within this middle layer again. And this is starting from the lowest form, this quantum foundation, where it's all about the actual quantum hardware access, so in the end providing the access to the hardware layer. And this then, I mean, including all of a couple of supporting functionalities like enterprise-grade qualities, scalability, security, etc. But also having a handle around the workload orchestration, so which job is routed to which hardware. Sometimes we could also simulate it on BTP itself, etc. And then, of course, I mean, also taking care of all of this cost management, routing it from the hardware vendors towards us, BTP towards the LOBs, towards the customers, and this then, in the end, automated, that we can also then deploy the solutions at a certain point in time live. And then we currently foresee that there's then two additional layers on top. I mean, the first one is focused on this persona of this quantum developer, where we say, I mean, this is the person who's really interested to, in the end, develop its own algorithms, develop its own code, potentially also go down to the circuit level. For him, we definitely need to provide some kind of development environment. And this is then in the end where it also gets tricky, because this is not exclusive now to this middle layer. For pretty much all of the capabilities you see in here, there are already existing solutions in place. So we have development tools at SAP running on BTP. We have a great optimization solution in place. We have a great machine learning solution in place. And we need to see, how we can get these two worlds together, the existing world and then the quantum world. Because it does not make sense to simply build yet another solution completely separate and not integrated. Then it will, of course, add complexity in order to not reduce the complexity. And what we try to provide, for this content developers, on the one hand side, of course, we need to provide some kind of coding environment so that you can actually code. We are also heavily thinking about, this idea of this reusable building blocks, so that you do not need to start from scratch, but rather can pick and choose and quickly iterate on new additional use cases. And this building blocks can rank really from smallest pieces, like, for example, encoding of a machine learning data set towards entire libraries, or even the largest extent potentially to some kind of sample project for an optimization machine learning algorithm, where we would say, it maybe fits for your use case 80%, so a lot of customers could directly pick it, deploy it, and use it. But if you want to then really squeeze the last 1% out of the service, you would like to get your custom objectives in, or custom constraints, or whatever, you could then simply take it, extend it, and then also deploy it without having the need to start from scratch. What we mean with this golden path is, this is already an existing concept to say within the world of SAP. It's in the end how our best practices and how we build cloud-scale enterprise applications. There's then two different approaches via CAP or RAP. RAP is then focused on ABAP, which is the programming language of SAP, and CAP then more the cloud-focused world, whereas RAP is also available on the cloud. And of course, we need to extend this then with best practices on how quantum should actually be integrated. But we also say, we can't stop here, because the quantum developer is really a persona which is not broadly or widely available. It's a certain experts which exist, and of course, the group is always extending, luckily. But in order to really scale it, then also within SAP, we say, we would even need to add yet another abstraction layer, which we then speak about this reusable business service, so that you could ideally simply rely on a service, so in the end an API, provide your data, train your machine learning model, and then do your inference then afterwards based on it. The question is, of course, how far we will come to that we can really then also build this standardized services, because there's always a trade-off between standardized solution which fits maybe a large amount of customers, but it's not really then the highest performance, and then having the need for extensibility. But I think this is then also something where we as SAP have a good experience on how to define this kind of standard-based level, and then provide the needed extensibility or configuration on top, as this is then also relevant for all of the standard classical applications we're building. And here you would see a quick overview about the use cases we are currently working on. Also here, it's in a varying majority, from early ideation towards POC, prototypes. And one of them, which is the tabular data generation, that's what we will then focus on in the next point. And I also now won't simply go through all of the lists. If you have questions to the one or other, then please approach me afterwards. I'm happy to discuss them. The key thing what we are also trying to focus on is that we are focusing more on these use case clusters, because only coming up. Because what we are focusing on is really trying to identify, at least now also with the head of this platform, which we are as BTP, on that we're really trying to find this use case cluster, so that we do not build at least this first level for use cases which might only fit one LOB or one customer, but rather try to consider them as some kind of use case cluster, so that you could, for example, this time series forecasting, it's a simple example, but this you could then use for price predictions in procurement, sales forecast, demand forecast in sales, potentially then predictive maintenance in manufacturing, etc. And likewise also for anomaly detection. I mean, there are so many applications available, from sales anomalies, observability of your data center towards fraud detection, etc. And the last slide I have on my side before I then hand over to Pallavi is very also here high-level architecture, where we also need to define a lot of details. But that's how we could currently foresee it. And on the left-hand side, once again, you see the actual business applications of SAP. And on the right-hand side, then the quantum hardware, where then also to a certain extent the system software would be part of. And in a nutshell, I mean, how this would work, you start at the business application, you then have the services being deployed, and maybe one additional comment, I mean, what is neglected in here is then this second layer, which is the development tooling. So this is in the end the consumption view. When your developed service would anyway, you deployed it your own, or it would already be provided by SAP. And we say, I mean, that the business applications would then call these quantum business services, then transform the actual business data, so the application model, to some kind of quantum or algorithmic model. And then in the end, in the background, call the quantum foundation, which is this third layer, where we would then take care of job scheduling, token management, everything regarding authentication, etc. And then, I mean, this is maybe the biggest question mark we're having, this vendor proxies, where we have the idea that in an ideal world, of course, I mean, you could here create these algorithms platform agnostic, and then in the end do some kind of magic and then route it to the actual hardware, and then get a good performance. But I mean, we of course know that this is by far not possible yet. So we are also at the moment rather here already having, to a certain extent, this hardware specifications, but the idea is that we really try to push it to the lower levels as far as possible. Could be that it then resides in the quantum platform. Sometimes it would also potentially make sense to even push this out further towards the actual hardware or towards the system software provider. But that's, I mean, one of the questions we are also discussing. And then, of course, I mean, when you have the job, it would then actually run on quantum hardware, or what we also do already now, then in the end simply deploying different simulators on BTP, so that you also have a low-cost environment that you can quickly test and iterate before you then actually send it to the actual hardware. And the benefit of course, I mean, when we develop it on BTP, we are in the SAP ecosystem, which means, I mean, we get a lot of basic functionalities which are needed for enterprise applications out of the box, like identity access management, commercialization, multi-tenancy, error notification, logging, etc. I mean, there's a lot more you need to consider. So it's only a subset, of course. I mean, but the good thing is, I mean, if we really put it close towards SAP and towards the business applications, we could really then have a proper integration and do not need to care about this core service to a certain extent. And with that, I hand over to Pallavi for the second part.
Thank you, Max, and thank you for waiting for my microphone installation. Okay, I'll try. So I'm gonna actually focus on one of the use case which we have developed. So we simply chose this use case because it's quite ahead. So we have built an end-to-end pipeline for this. Yeah, so why tabular data? Over 80% of enterprise data is in structured formats. So enterprises like SAP. And tabular data often contains a mixture of categorical and numerical features. Therefore, it's a bit of a hard task for generative modeling. And it is also quite fitting use case for SAP because SAP is already working on some foundational models for structured data. So this problem of learning probability distributions given a specific data set is a very relevant problem for SAP at this point of time. And what are the relevant use cases of synthetic tabular data? It's very beneficial for downstream machine learning tasks like data privacy and anonymization, Data augmentation, when you have a class imbalancing problem in your data set in machine learning tasks, you can actually use synthetic data for data imputation and balance the class and improve the performance of your machine learning model. You can also generate the same synthetic data, retaining the similar statistical properties for data privacy and anonymization reasons, but you can also tweak data. You can change the characteristics of data, generate new data sets for data augmentation, which can also be useful for life sciences or drug discovery tasks. So these are the typical capabilities and reasons why this tabular data generation is a relevant use case for SAP. Just the research motivation. So our objective here is actually to employ some quantum variational algorithm to learn heterogeneous tabular data with similar statistical properties and distribution, and benchmark it against classical state-of-the-art tabular GAN models. And this is our effort to do that. Right. So we have developed a quantum generator model to learn the distribution of training data by adapting the classical GAN architecture. The GAN architecture we use here is adapted from the classical machine learning models, and this is a hybrid classical model. That means that there will be two networks in place, and one of them is classical and other one is quantum. Right. So what are GANs actually? So there are different variants exist. So in the classical domain, we have basically two neural networks, generator and discriminator. The task of the generator is to generate samples or to generate data, while the task of the discriminator is to classify whether the generated sample is fake or real. So it's based on a min-max theory. So generator typically samples from a random distribution, let's say Gaussian distribution, and then passes on to the discriminator. Discriminator is trained on the real data as well as trained on the generated samples. And discriminator has a relatively simple task of classification, whether it's a real sample or a fake sample. This is a very similar setup which we adapted for a quantum algorithm. We just replaced the classical generator with the quantum generator. So in this case, we employ a quantum circuit to learn argument probability distribution, and then measurements, and then the result is passed to the classical neural network, which does its own job. And in variant 2, both the networks, generator and discriminator, both are quantum, but we have not focused on that. We have focused on variant 1, so it is a quantum classical hybrid algorithm. Right. So what is the typical pipeline for it? So you have some kind of latent space or some kind of sample probability distribution. You sample it and pass on to the generator. Generator encodes and processes the data. Then we take the measurement. Then we pass that to the discriminator. Discriminator is also trained on the real classical data, and then discriminator will then just produce some output. That output, the cost function will be calculated on that output, and based on that, we employ a classical optimization algorithm to update the parameters of the generator and discriminator. Variational algorithm, a typical setting. Right. What are the benchmarks for this? So the classical benchmarks which we have chosen, the left one is conditional GAN. It came from MIT, and the other one is from Imperial College London. So they are quite state-of-the-art classical models for the same objective or for the same task. And we have actually used a third-party library for evaluation of our results. We have also trained home-built vanilla GAN ourselves, but If you know something about GANs, the problem with GANs is that they collapse at some point of time. They try to create one particular category, and there are numerous problems with that. That's why these models are actually offer some kind of improvement and produce better results with GANs. So we chose these two classical benchmarks. Right. So what are exactly our data set? We have not used any synthetic data set, rather we have used public data sets, which is actually used in classical machine learning experiments as well. So adult census data and electronic health records data. So Mimic Health is electronic health record data, and adult census is just a census data. Well, and how did we process this data set? So as you can see, here we have different features in this case, numerical as well as categorical features. So we have binned the numerical features and binarized it to form a bit string. We have done a very similar thing with the categorical variables. So binary categorical variables are not one-hot encoded, but other categorical variables which have more than two categories are one-hot encoded. And then we have divided these into sub-registers. So a circuit is typically formed with all these sub-registers. So we have created a standardized data sets with 10, 15, and 20 qubits. So that leaves to actually 6 data sets. And these 6 data sets will then be chosen for our experimental setup. Well, I can't really disclose you the entire circuit yet because it's still under process for publication. But the idea is that we have numerical as well as categorical columns. And a numerical column is numerical features are binarized and will be passed in some sub-register. So each feature actually has its own sub-register and corresponding gates. And then we form entangling layers to entangle these sub-registers. These entanglement between the sub-registers and entanglement within a register. So global and local entanglement, and then we measure them. So after measuring, we do a bit of post-processing. That means we then take out the bits which corresponds to the numerical features and bits which corresponds to the categorical feature, and then we employ some validation mechanism to check whether the bit string corresponds to a particular categorical feature is valid or invalid. It should be valid as per the one-hot encoding. So if the one-hot encoding is 010, other solutions will be discarded. But our circuit is actually built in a way that it enforces symmetry of some sort. That means it only operates in subspace, not in the entire space. So what does that mean? That means that we initialize the circuit, for example, categorical circuit, and the one-hot encoding for a particular categorical variable is, for example, 010, and all other encodings we just discarded for a particular categoric feature. So we operate in a very defined sample space or subspace. Right. Then we trained our model on these data sets, and on the left you see that we have 2 metrics, KL divergence. KL divergence computes the divergence between 2 probability distributions. Here our first probability distribution is original data, and then the second one is synthetic data. So it's better if it is lower. On the other hand, pair metric came from MIT library, from third-party library. It is an average over different metrics. So what we are interested in here is checking whether marginal distributions are correct, like one-dimensional distributions are correct, and whether the two-dimensional distributions or joint probability distribution is in place. So for marginal distribution, we use total variance distance, and for other correlation or pair trends, we use different metrics and take the average, and the overall metric should be higher, and it denotes the same thing, similarity between two probability distributions. Both are in complement of each other, but the task is very same. And on the right-hand side, you can see the loss function for our training. It seems like it's converging, right? But discriminator's loss is a bit higher, is an indication that it needs a bit more training. Typically, numerical architecture or circuit needs more training than the categorical sub-circuit, which has an effect on the training as well. So here, typically, we see that it's the possibility that it is under-trained. We can train it more. But it produces actually a good score overall, preceding classical GANs. So, right. And then the next slide, on the left-hand side, you see that there are 4 data sets. We have not conducted yet experiments with more than 20 qubits or with 20 qubits. We have just conducted experiments for 10 and 15 qubits. And green dots are actually our own tabular quantum GAN, and others are state-of-the-art classical ones. And you can see here clearly our tabular GAN performed better than the classical GANs. On the other hand side, this reflects that when we increase the circuit depth of the circuit, there is not really a major performance improvement, although you can see the variance is quite high here. So even if we train with only circuit depth 1 in our case, it still produces, optimal score or metric or result. Right, our QGAN performed it better than our classical benchmarks. A detailed analysis on multiple factors are still in progress. These are the initial results of our experiments. And right, so the complete pipeline in our case, for pre-processing, we have selected some features based on the correlations among different features. And then we binned the numeric data, aggregated the categorical data into some categories, because each category contributes to 1 qubit, so we can't really process all the categories, so aggregation is a necessary step here. And then we calculate the needed qubits, the amount of qubits we need here. For encoding, we do one-hot encode our categorical data, but we binarize our numerical data. Our trainings, we have typically performed our training on simulators. We have used actually AWS density metric simulator and also state vector simulators for the training. Implementation is done in Penny and Qiskit, and inference is only quantum generator is used for the inference, and right. So we also ran inference on BTP and AWS. This is the middle layer, which Max already talked about, but after inference or typically after training, we have to decode our data so that we can evaluate, and then some sort of post-processing for evaluating our generated samples or checking the quality of our synthetic data. Right. This was all about this use case and the experiments related to this and results. So next step is, so we have started to build these demos or prototypes of all the services or all the use cases we built, and then I will actually take you to the demo of this tabular data generation. It is still work in progress. No way we are done. But we can show something. I can't show, right? It always goes to the first screen. Right. So Right, so the homepage is, so we have actually working on different use cases here, but the one which we discussed here is tabular data generation. In this case, you have uploaded some original data, and then you can just click on generate samples to generate some samples from our already trained models. The model is already pre-trained. And you can here actually visualize the distribution of your generated as well as the original data. Here you can see that it's not really perfect, but it indicates some learning that our model actually has learned at least. Well, these age ranges corresponds to the binned data here. So, you cannot really map exactly bin IDs to the actual age. You need a different mechanism for that, but at least we show here the age ranges generated. And right, if you want to check for the categorical data, how well it learned over the categorical data, you can see that the learning is pretty decent here as well. Right, this is it for the demo. And then I will share the slides again. And what are the key takeaways? So our major focus is to identify SAP relevant use cases or quantum computing use cases for SAP and invest in quantum computing, but our major focus is quantum machine learning and optimization. And we are already working on defining an architecture for quantum and hybrid workflows. Our use cases, typically tabular data generation or time series forecasting, is still work in progress. They are not ready for the production. And we are open for further collaborations and engagements. So this is it from us, I guess.